All right, section 1.3 continues our discussion of limits. So last section in 1.2, we looked at limits in two ways. Do you guys remember what they were? How did we look at limits? What was that? We did it from the left and the right. That's true. We did it with, how did we visually do it? Graphing was one, and tables, numerical was the other. Yeah. So we've done it in two ways. One, by looking at a graph, and two, by looking at a table, sort of a numerical discussion. And so today what we're going to do is we're going to do this from an algebraic point of view. So first, some basic limits. So we're going to have some limit properties. That's what we're going to discuss first. So the first limit property is that if you have the limit as x approaches a of a constant, then the limit is just the constant. And that should make perfect sense from a graphical point of view, and I'll justify some of these from a graphical point of view because they're very easy to sort of argue about. If this is the value c, and this is your equation, that is it's y equals c, then the line y equals c is this horizontal line. So as you can see everywhere on the line, the y value is the same, so the limit is the same no matter what a value you're looking at. You're getting the same y value. Okay. The second one, if you have the limit as x approaches a of x, that's just a. And again, from a graph point of view, this is the line y equal x, right? These are all just equations in terms of y equals. So the line y equal x looks like what? You guys remember? Okay, so slope of what? One, a slope of 1, and a y-intercept of 0, right? So it looks like this. It's a 45-degree angle, if you're thinking about some things maybe from trig or something like this. So if you're at an x value of a and the equation is y equal x, then the corresponding y value is also at a. And that's all it is. So that's from a graphical point of view why that would sort of resonate with us. All right, the next four are a little bit more detailed, and I'll give you a chance to have a little bit of writing to get all these written down. So we're going to suppose that the limits for f of x and g of x both exist, and c is a constant, and then the following rules or properties would apply. So if you have the limit of a constant times a function, that's number one, then in essence you can sort of pull the constant out in front of the function, and you can talk about the limit of the value itself. So that's a property of limits. This had this ability, if you will, to move the c on the outside. The second one says that if you have the limit of a sum or a difference, then it's the sum or the difference of the limits. It's what you would want to be true, and it is. You can take it and you can look at it piecewise, and each of the pieces you can find out their answer, and then you can just push them back together with the sum or the subtraction, depending on which one you're working with that you had originally. Third one, same kind of thing, multiplication. If you multiply two functions and you take their limit, it's the same thing as taking the limit of each of the individual functions. Again, all this only works if the limits exist. If the limits are just does not exist kind of things, we got other weird things could happen, okay? So the limits have to exist. And then the last one, number 4, is about division. So you see f of x over g of x, and you can separate the division of the limits. There is an additional consideration down here, or a constraint. It says the limit of g of x cannot equal 0. Why would that be there? Yeah, we can't have the denominator 0, right? So if this limit actually were 0, we couldn't use this property in this way. That's all it's saying. Okay. All right, so are those actually typed into your notes at this point? Some of you are not writing, so I'm thinking maybe I changed my notes at some point. Are they in there? Yeah. Excellent. Man, I'm ahead of myself. I had no idea. Okay. So we're going to actually find some limits. Now, the practice of what we're doing, let me actually show you how the first one works out sort of longhand, if you will. And then I'm going to show you in reality what we're able to do shorthand because of those facts. Are you guys ready? Okay, so let me write the first one down. You can write it down with me. After you write this first one down with me, did it print funny on this? Like this?
It printed like the sides.
I need to fix that. Hang on. All right, I'll get those fixed later. All right, so this is the way these properties actually work. So that's what I'm going to do first. The first thing is you notice there's addition, correct? So the fact that there's addition means that I can separate this, and I'm only going to do one of these longhand like this. Okay, so just humor me for the moment and write it out. Okay, you can separate this with the limit of negative x squared and then the limit of 1 as x approaches 1, because that's the limit or the x value on the bottom. Okay. And then what does x squared mean? I mean, we didn't have a property over here that said anything about squares. It means x times x. So this is really just property number 3, right? It looks a little bit different, but it's just property number 3. And this negative right here is just a -1, agreed? So I'm going to do kind of 2 steps at once to save myself a little bit. I'm going to pull this negative out in front. And then this is the limit as x approaches 1 of x times the limit as x approaches 1 of x, because it was x times x is what you told me. And then I still have plus the limit as x approaches 1 of 1. So this is really what all of these properties tell us we can do. We can sort of break it down into all of these pieces. Because we can break it down in all of these pieces, then we can apply basically properties 1 and 2 that were at the very beginning. The sum basic limits part right here that looked like these. Oops, I went too far. These. Right? The first one, the limit of a constant, well, that's my limit of 1. And the second one, limit of x, that's my limit of x. So I can use both of those in this argument now. So the negative stays. What is the limit of x as x approaches 1? It's 1, right? That's property number 2 from the very beginning. And I've got that twice. What's the limit as x approaches 1 of 1? Also 1, right? My 1s are looking a little funky today. So we have negative of 1 times 1, which would be 1. And then I had the negative in front, so I have -1, right? And then plus the 1 at the end, which means that the total result of all the work here is 0. Okay. So I'll erase that piece in a minute, but let me sort of jump to the fun part of how this actually works in reality. And some of you have had some calculus before, you know this. Because we have the ability to do what I just did and break things apart in all these pieces, because we have that ability, what we can actually do is we can actually take the value that we were given to begin with, this x equals 1, and we can just evaluate our function at it when it works. Okay? And I'll show you very quickly when it doesn't work. So that's not a mystery kind of thing. Just hold tight for that. But if we have the ability to just plug it in, we can. So that means we could take negative 1 squared plus 1 on this problem, and we could get our answer of 0 without actually showing all the steps of the limit process in the middle. But it's because of that limit process that we're able to do that. Are you guys tracking with me? Does this make sense? Okay, so let's try the same thing with number 2. That is, we're going to try this sort of shortcut where we can just plug the value in and see if it works. Now we'll just keep seeing if it works, and if it doesn't work, then I'll show you what we do secondly. Okay? All right, I'm going to take part of this work off so I've got some space. Excellent. So if it's going to work, it means that we can just plug the value -3 in for all our x's. So I have 2 times -3 minus 3 over -3 plus 5. If it's going to not work, it's probably not going to not work in the denominator. That is, the denominator would end up being what? 0. Is this denominator going to be 0? No. So we're probably going to be okay. What is this denominator going to be? 2. Great. How about the numerator? -9. And it is perfectly fine because that it is in a reduced fractional form to leave it that way. Not a fan of mixed numbers, so they're not helpful to use once you get to math at this level. So -9/2 is perfectly fine. Any questions? This is just evaluation at this point, right? Okay. Now this one looks a little bit different. This one is what we call a piecewise function. I'm not going to graph it, although we could graph the thing and we could actually take a look at what's happening, and we may want to look at that in a little bit. But there are 3 lines of information. This first piece of information is going to only be true when the x values are less than 1. Right? So this is the portion of the graph where x is less than 1. And then the second equation, that is f of x equals 3, is only going to be true on the middle portion of the graph where you're between -1 and +1. And then the third piece of information is only going to be true where on the last piece of the graph where x is greater than 1. Okay, so I've got 3 pieces of my graph sort of split into spots, and I'm going to follow whichever equation it is that matters for that piece of information. So taking a look at the limit that we're looking at for our function, it's the limit as x approaches the positive 1. So which piece or pieces of the graph apply to x values that are at or around 1? The second and the third. Because this is for when x is less than 1, and this is for when x is greater than 1. The first piece of information is less than negative 1. That's not near positive 1, so it doesn't apply. Okay? Now, one of you guys said that last section we talked about limits from both directions. Do you remember that? Well, we don't have to worry too much from limits of both directions when the graph is all connected. We call that continuous. This graph may or may not be continuous because it's in pieces. So we have to start worrying about those one-sided limits again. So we're going to take a look at 2 one-sided limits. We're going to look at the limit as x approaches 1 from the left, and we're going to look at the limit as x approaches 1 from the right. Now, limits have no meaning unless you put the function next to them, so we will just call this function f of x. If you want to put the piece of the function you're on, you could do that as well. All right, so if we're looking as x approaches 1 from the left, which line, second or third line, are we on of our function? Which of these 2 right here is the function if we're on the left side of 1? The second one, right? Left side would mean smaller than the value 1. So this function right here, I'll write out one more step of it just to sort of emphasize the fact. Because we're on the left side of 1, we're looking at the x value, or the function which has the equation, if you will, 3. On the other one, if I'm on the right-hand side of 1, what part of this am I on? Which line, second or third? On the third line. So this one's function is actually, or equation at that point on the graph is 2x plus 1. Again, as x approaches 1 from the right. Now, once we identify where we're sort of, getting the values from, it works the same way. I still just plug numbers in, okay? So the first one, of course, the limit as x approaches negative, or 1 from the left of 3 is just going to be the number 3. It's always 3 on that piece. On the second one, we're actually going to plug the number 1 into the equation. So 2 times 1 plus 1, and we end up getting 3. So what we discovered last section was that if the one-sided limits, that is the limit from the left and the limit from the right, are the same, then the limit exists. So this actually does have a limit value. So the limit as x approaches 1, actually, of our function, is in fact 3. Now, if I instead had not gotten 3 on both of them, one of them had been 3 and one of them had been something other than 3, what would happen then? Then we see the limit does not exist. Okay? But the actual physical plugging in of values is exactly the same. So the plus or the minus part of this, right in here, only tells us which line of the equations we're working on, or which equation in the pieces that we're looking at. Okay? All right, we're going to do another example here. So since you guys have it printed out the way I have it, we'll just go through these pretty quickly. For any polynomial p of x and any real number a, the limit as x approaches a of the polynomial is simply evaluating the polynomial at the value of a. That worked for x squared just a moment ago, right? All we did was just plug the number 1 in, and so it works the same way for all polynomials. So let's just take a moment to remind ourselves what polynomial means. I know you guys know this, but just a reminder. Polynomial is sums and differences, okay, so you can have pluses and minuses, of variables raised to powers. The powers have to be whole numbers, okay? They can't be negative powers, they can't be square root powers or decimal powers, none of that crazy stuff going on, okay? None of those things. And the coefficients could be anything you want. So you might have something that looks like 4x cubed plus 2x minus 7. That would be a polynomial, okay? But again, the 4, the 2, the 7, those could be any kind of number you'd like, any real number. The exponents themselves are the parts that I'm worrying about being whole numbers. And the value 7 is a polynomial as well, because even though it's not written in there, the reality is that this is x to the 0, right? And 0 is a whole number. So we have constants that are allowed to happen here too. The second one talks about what happens when you have a square root, or in general actually an nth root. So just a minute ago I excluded the possibility of having exponents that were fractions. Well, if you do have an exponent that's a fraction, then it can be written in radical form like this, and as a decimal would be the same way. So if you had the nth root of something, so like a square root or a cube root or something like that, you could take the limit of the function first and take the power afterwards. So you could do that sort of in reverse order. That will only work if the limit value is positive when the n value is even. So just as a reminder, what that's saying is that if you have a square root, you only can have positive things underneath the square root, right, or 0. So that's what this is hitting on, is that anytime you have an even root, so if you have a square root, a fourth root, a sixth root, then the values underneath the radical, the limit value, would actually have to be positive for this to work. Okay? All right, let's take a look at some examples where a few of these things come about. Not all of them right now, but... All right, here's the first one. Example. Find the limit if it exists, which is probably going to be telling you that somewhere along the way we're going to see something not existing, right? All right, so we try the same thing we always tried before. We try plugging in the number, because if that works, that's the easiest way to do it, okay? Don't go trying to reduce things that don't need to be reduced. Just because something factors and simplifies, if you didn't need to factor it and simplify it, you're wasting your time. So try to see if the numbers work first. So this is plugging in the x value of 3. So I'd have 3 minus 3, which would be fine. That's not a problem, agreed? I can have 0 on top. And then I have 3 squared minus 9, and that gives me 0, and that is a problem, because I can't have 0 in the denominator. Everybody good with that so far? So this method is not going to work here. I got a 0 in the denominator. And that sort of fails the condition of part 4 on that limits properties sheet we looked at before. So what we're going to do, and we talked about this last time, we didn't actually do it, we talked about it being the case, is we're going to factor. But I want to make sure you're being very persistent with your notation. This limit as x approaches 3 is going to be on every step of this problem until you physically plug the number 3 in for x. Okay? Don't leave it off, because what you're doing is you're writing a line of things that are equal. In order for it to be equal, the limit still has to be there. All right, so what we're going to do is we're going to factor the denominator. So that's an algebra idea. X squared minus 9, how does that factor? Very good. X minus 3 and x plus 3. Now, why did we want to factor this? What's our goal here? To reduce something, and hopefully in reducing something, the denominator will no longer be 0 when I plug 3 in, right? Okay. Now, the denominator, neither of those pieces of the denominator is exactly the same as the numerator, but there's one of them that's very, very close. Which one's actually very, very close? Do you know? The first one actually is, yeah. The only difference between this and this is that the negatives are on the wrong pieces, or on different pieces, right? The first one is 3 minus x, the second one is x minus 3. The negative and the positive are switched. Everybody make sense of that? So we can reduce those, we can cancel them out, but when we do, we cancel them out and we get a negative 1 out of it. All right, it's like having a 5 on top and a negative 5 on bottom. Can you cancel those? Well, of course, but you're going to get a negative out of it when you do that, because they're exactly the same expression, but the sign is opposite. It's the opposite sign. So these two are going to reduce, but when they reduce, I'm going to get a negative 1. Put it wherever you'd like. I'll put it on top. Now, I'm going to take one more step just to clean this up, because this looks kind of messy at this point. I've got now the limit as x approaches 3 of negative 1 over x plus 3. I've reduced all I can, so now we're going to try and plug the value in and see if it works now. So I've got negative 1 on top. What happens when I plug the number in on bottom? You get a 6. And that works just fine. Now, when we actually have this ability to cancel that out, and it removes that 0 in the denominator, we talked about this before, what happened on the graph visually? Do you remember what the visual image is? Do you remember? There's a hole in the graph. Okay? So we actually will have a hole in the graph at this x equals, or x approaching 3 value at x equals 3. There's a hole there. Now you can't see that if you graph it because your calculator pixelates things and so forth, so it doesn't draw, a hole in there. But if you trace along there and you actually end up landing on x equals 3, it won't give you a value. There will be a hole in the graph at that point. Okay? All right, let's try the second one. Give it a shot. Let's try plugging the number in. 4 squared minus 5 times 4 plus 4 over 4 squared minus 2 times 4 minus 8. What do you get? What's on top? 0, which is fine. There's nothing wrong with that. What's on bottom? 0, and that's what causes our problem, right? So if you wanted to, you could just check the denominator. Okay, you don't have to necessarily check the numerator. But we do, in fact, have a 0 in the denominator, so our best and only option at this point, algebraically, to do this would be to see if this actually will factor for us. So we're going to limit as x approaches 4, and we're going to attempt to factor, and in this case, we have to factor the numerator and the denominator. All right, so then, let me give you one quick bit of advice. If it's going to reduce in a helpful way, it has to reduce so that it eliminates the problem at the value 4, right? I mean, that's where our problem is. So if this is going to work, there better be an x minus 4 factor in here that reduces on top and bottom. Otherwise, it's not going to work anyway. So you can kind of give yourself a little bit of a head start. This isn't a terribly complicated one to factor, I understand that. But sometimes they're not so pretty. Okay? So if I have an x minus 4 factor on top, what's the other factor going to be? X minus 1. And that does, in fact, give me the minus 5 in the middle, right? Okay. In the denominator, if I have an x minus 4, what's the other factor? X plus 2, yes. That gives me negative 8 at the end, and that gives me a negative 2 in the middle, right? All right, so that's good because we needed the x minus 4, otherwise the problem, doesn't work as we've been looking at them. So now I have the limit as x approaches 4 of x minus 1 over x plus 2. So if I plug in the number 4 on top, what do I get? 3. And on bottom? 6, which reduces to the fraction 1/2. Okay? It all culminates right here. I don't think we actually have to do much to look at this and say, yep, there's a 0 in the denominator, right? Yeah. So now what? Because I don't know about you, but that also doesn't look like something that I'm comfortable or familiar with factoring, right? So what do? Well, we do something that you probably have never seen done before for this, well, certainly not for this purpose, but maybe in this way. What we're going to do is we're going to do something called rationalize. That word you're familiar with. But you're used to rationalizing what? The denominator. And we're going to rationalize the numerator. Okay, so this is a very common process when we've got radicals, rationalizing the numerator. Okay, so how do we rationalize the numerator? Well, we use something called a conjugate. Have you guys remember conjugate? The conjugate of square root of well, the conjugate of, let's say it this way, the conjugate of a plus b would be what? Do you remember? A minus b. So it's the same values in the two locations, it just switches the sign in the middle. And so that's sort of the conjugate no matter what you're working with. Here we're working with radicals. So I'm going to multiply by the conjugate, so that's square root of 2 plus x. And then instead of a minus between, I'm going to put a plus, and then square root of 2. But if I do that operation and multiply that through the numerator,
you have to multiply it in the bottom.
You do. You have to multiply it through the denominator as well on the bottom. Now, before you look at that and think, oh my word, there's a lot of multiplying, bear with me, there's really not that much. So the reason conjugates work so nicely to rationalize is because It really is because there's a difference of squares here. This piece right here, when I multiply the inside terms, and this piece right here, if I multiply the outside terms, are exactly the same but opposite signs, right? So I do not get any inside or outside terms. That is the reason for using this method. No inside, no outside. But I do get the first terms multiplied. But what happens when you multiply those two first terms together?
The square root.
The square root goes away, yeah. So I really just have 2 plus x. And then I need to multiply the second pieces together. But again, they're much alike. So when I multiply the square root of 2 times the square root of 2, I get 2. And the sign that goes between these two is what? A minus, because one was minus and one was plus. So the numerator simply, and this always happens. I mean, that's the whole point, is that it's going to work every time. We've created it to be that way on purpose. And then in the denominator, while you might be tempted to sort of distribute the x through this, I would encourage you not to. Just leave this written as x, parenthesis, square root 2 plus x, plus the square root of 2. Just leave it all ugly. Okay? Let's go back to that numerator. What do you see happening next in that numerator? Something. It's going to be just x. Why? Yeah, this is a positive 2, this is a negative 2, so those are going to reduce to 0. So I'm just going to get x, okay? And then what happens? The x is canceled, which is exactly why I didn't want you to distribute it, because it's going to go away anyway. This x and this x cancel. Yes, they do. So we end up with the limit. What does that leave us on top? A 1. Don't forget that fact. And then I've got the square root of 2 plus x in the bottom plus the square root of 2. Now this is a little bit still kind of ugly. I do need to plug in the value of 0. So I do in fact get square roots still in my problem. Looks like that, right? So what happens when I add the square root of 2 plus the square root of 2? What is it? You have 2 root 2, right? There's 2 of them, so it's 2 root 2. And we will rationalize that. It's going to clean up really nicely. So what would I need to multiply the denominator by to get rid of the square root 2? Square root 2, right? And if I do it to the bottom, I'll do it to the top. So on top I get square root 2. What do I get on bottom? I get 4. So the final answer is square root 2 over 4. Now let me pause for a moment and just kind of point something out to you. All the problems we've done prior to this one didn't have like radicals in it. They were all just whole numbers or fractions. You could actually do any of those problems with that numerical process, right, and to check yourself. So if you wanted a secondary way to make sure you got the right answer, you could check yourself with that. This is going to be a little bit more difficult. You could check your answer, but you couldn't get this answer using the numerical approach, right? Because your calculator is going to give you decimals for this, not a square root over 4, correct? So you could still check to make sure that the decimals that it gives you is equivalent to this decimal that this would give you if you figured out what it was, but you couldn't actually go from a decimal form into this form. All right, a little bit of trig. Any real numbers, a, we have the limit as x approaches a of sine of x is sine of a, and cosine of x is cosine of a. You're just evaluating by plugging in the value that you're working with as x approaches that value. And then the last one on this slide is a very interesting one. You don't get to prove any of this one right here. This is definitely not a definitional kind of thing that I'm giving you on the last one. There is a proof that follows with this, but you do not have the calculus to be able to understand the proof yet for this. It comes in Calc 2, I think. So just for now, understand that on this one, if you tried to plug in 0 and you got sine of 0, that'd be 0. And if you tried to plug in 0 on the bottom, you'd get 0. So if you actually tried to plug this in, you'd get 0 over 0, which is obviously, we call it indeterminate form. You can't have the 0 in the denominator. Well, it actually does have a value. Its limit actually is the number 1, and there is proof to be done to verify that. But for now, just recognize that fact. So if you see sine x over x, its limit value is 1. Okay? And I'm sorry, I didn't emphasize this, but this is as x approaches 0. It doesn't work for just any x value. If you had x approaches pi, it wouldn't even matter, right? Because pi in the denominator is not a problem. Okay, so let's take a couple of examples with this one. All right, the first one says we have the limit of sine. Oh, I switched my paper before I meant to. We have the limit of sine of pi x over 2 as x approaches 2. So what are we going to do for this one? Yeah, we're just going to plug in 2, right? That's the very first one that we did on the last slide about sine x. So we can actually just evaluate this by putting the 2 in for the x. So this is the limit. I'm sorry, I didn't mean to say limit. Sine is what I meant to say. This is the sine of 2 pi, if you will, over 2, or pi times 2 over 2. The 2's, of course, reduce, so you get the sine of pi. What's the sine of pi? That's 0. Okay. Second one, the limit as x approaches 5 pi over 6 of cosine of x would be cosine of 5 pi over 6. And I know many of you had trig last semester, and this is a unit circle value, right? What's the cosine value at 5 pi over 6?
0.866.
In radical form, though. Do you know what it is in radicals? Because that's where we got the unit circle stuff from. There is a square root. What is it?
Root 3 over 2.
Yes, root 3 over 2. Yeah, and if you type in root 3 over 2 into your calculator, Christian, it will tell you that same decimal that you just told me. So you might want a unit circle handy if you're a little bit unfamiliar with that. I know not all of you took trig last semester. Many of you did, but not all of you did. So refresh yourselves on unit circle kind of stuff. I know some of you are shaking your heads. But we're going to have to know that unit circle when it comes to the first exam, okay? So use it if you need to for now with your homework, but we will need to have those memorized for the first exam. So this is square root of 3 over 2. Positive or negative? I didn't even let you guys tell me.
Negative.
It is a negative. Yeah, this one's a negative. That doesn't look very clear. Let's try that. Negative. There we go. Negative square root of 3 over 2. All right, let's try another one. Again, limit, if it exists, we have the limit as x approaches 0 of sine of x over 5x. There's going to be a 1. We're not going to end up having a 0. If we try to put the 0 in, we'd have a 0 in the denominator, right? This looks a little bit like that special trig one that I gave you, but not exactly. What's different about it? The 5 in the denominator. But here's what I want you to recognize, and I know that you know it's true, you just may not see it when you first look at it. That 5 in the denominator is the same thing as having 1/5 times sine x over x, correct? And that's what 5 in the denominator means. And you have a property of limits that says that 1/5 can be in the front instead of it being in there. It doesn't have any effect on the limit value itself, except as a multiplication factor. Oops. So I can take 1/5 of the limit as x approaches 0 of sine of x over x. Now then, what is the limit of sine of x over x? That's 1. So this ends up being 1/5 in essence times 1, or just 1/5. And you don't have to show every single one of those steps, but I also don't expect that you're going to do this. I do not want you to jump from there to 1/5 immediately. I want you to show a little bit of why that worked. Okay? Again, you don't have to show everything, but something in there should be shown. Now, you're definitely going to have to show me a little bit going on number 10. Cosine, tangent. I didn't tell you anything about cosines and tangents, did I? Actually, I get to cosines, not tangents. That's what I want to say. There's no property so far about tangents. And if you do try and plug zeros in everywhere on this one, you get a 0 in the denominator at the very least, which is unhelpful. So what we need to do is we need to do something with that numerator to simplify cosine of x times tangent of x. Any thoughts on that? What was that? Yeah, we can take tangent and we can rewrite it in a different way. Do you remember something, those of you who've had trig recently, called verifying identities or proving identities? That's kind of where this is headed. You'll have a lot more emphasis with that later in another section in Calc 2, not in Calc 1. But it's helpful for this, to remember then that tangent is sine over cosine. So right now, this is what I have. I have the cosine that was originally there times the sine over the cosine, and then divided by the x. And that's helpful because what happens next?
Cosine.
Yeah, the cosines cancel. And so I end up with the limit as x approaches 0. And it really ends up just being sine of x over x, which limit value is 1. But it didn't start out looking much like the number 1. It really didn't. So we had to do a little bit of recognition before we could get there. All right. Now this is a little bit different. This actually uses those properties of limits that I wrote out on the very first example to a pretty good extent. This one tells us that the limit of the function is 2 as x approaches a, and the limit of the function g of x is negative 3 as x approaches a. Okay? The function is not 2 or negative 3. The limit is. Okay, so the function may be doing all sorts of interesting other things, but at that one particular point, that's the y value, or it's the y value you're getting close to anyway. All right? So when you take a look at this down here, it says the limit as x approaches a of f of x squared over g of x. Yes, eventually we are going to take the function of f of x value and we're going to square it and we're going to divide it by the function g of x value, which was the negative 3, and we're going to have that on bottom. But we don't get to jump right there. We're going to use the limits to actually show that worked. Okay? So all we're doing is we're going to use those limit properties to separate these pieces out. And we've practiced with it once before. So one of the features that you see happening here is you see a division. So I can write this as division of limits. All right, that is one of my limit properties. As long as the limit value of g of x isn't 0, I can do that. And it's not, because we actually were given that value. And then how do we separate the numerator out? I've got something squared.
The limit of fx times the limit of...
Right, we separate it out with multiplication. So this is the limit of f of x times the limit of f of x. And both of those need to have the x approaches a underneath the limit, the LIM notation. Now, once it's in this form, I actually have the ability to substitute. I mean, that's what's going on here. What I'm doing is I'm recognizing that this piece right here is exactly this notation, which is why I'm allowed to substitute it in. And I can do it twice. So this is 2 times 2. And then the other one over here, down here, is the negative 3. So I end up getting what for my answer?
4/3.
Right, negative 4/3. All right. I want to take a look at one of our properties sort of in reverse. Number 12 says to give examples of functions f and g such that the limit of the function f of x plus g of x exists, but the limit of the individual functions do not exist. This looks an awful lot like where we started this morning, like the very, I don't know, the second slide or whatever. It looks an awful lot like this slide, number 2. Doesn't it? The difference is in what you know to be true. What you know to be true on this slide right here is that we start out being told that the two limits individually exist. Do you see that? And then that means that these two pieces, not that one, but these two pieces that we're working with right now, have the ability to be the same. If these limits did not exist, one or the other or both, then we would run into problems potentially down here. Okay? So we're going to basically do just that. We're going to create a function, f of x, and a function g of x, where the limit doesn't exist. But we're going to show that when we add things together, it actually works. All right. So let's start out with finding out a function, the limit of f of x, and the limit of g. Well, actually, I don't want to say limits right now. I need to change that. I want to find an f of x and a g of x. So think with me. How do we get, or when do we have, let me say it that way, when do we have limits that don't exist? What is happening on all these ones that we've seen pretty much today? Denominator is 0. I mean, when the denominator is 0, things don't work, right? So can we create something with a denominator of 0? Sure, we just need a variable in the denominator, right? So somebody create me something that's very nice, quick, and easy with a variable in the denominator. Simple. 2 over x, that would be great. 1 over x would work as well. If you want to do something super creative and do x minus 7 or something in the denominator, more power to you. Okay, here's the cool thing, though. What I want to do for g of x, well, let me make a point of talking about this. The a value we're approaching then here would be the a value of 0, right? The denominator is going to be 0 when the a value or the x value is 0, right? So when x approaches this value, we're going to have problems. Here's something cool. We're going to just let this be the same thing, but negative. Does the limit still not exist at x as x approaches 0? Yes, it still does not exist. But watch what wonderful thing happens here. The limit as x approaches 0 of f of x, which is 2 over x, plus g of x, which is negative 2 over x. What happened? Yeah, they cancel, giving us what value inside that bracket right now? 0. This is just the value of 0. So the sum of our two functions has a limit because the sum is just the number 0. What is the limit of 0 as x approaches 0? 0. Yes, the limit is 0. But the individual limits, okay, but the limit as x approaches 0 of 2 over x does not exist. And the limit as x approaches 0 of negative 2 over x does not exist. And I think there's one or maybe two examples where you get to create something that fails. So what you really want to start looking at when you're thinking about them is what things make this fail? How do I make it not work? And a lot of times zeros and denominators are a good place to start.